Is Dan Oak. I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos I've been posting on the Comp 444 forum up to this point, first of all, you're very patient, and second of all, hopefully you're learning something about Project 1, which is detailed in the SparkFun Inventors Kit guide that you can see right here. So for all students in Comp 44, you would have received this guide along with the actual kit that the guide is associated with, the SparkFun Inventors Kit. And so I've done circuits 1A, 1B, and 1C associated with Project 1 so far, and now we're going to go on to 1D in this video. So the last project we did was 1C, which was we added a photoresistor to our circuit, and basically as we decreased the light level, the LED turned on, and in high light conditions the LED turned off. So we essentially created a night light that automatically turned on in dark conditions. And then we did the coding challenges associated with that, and what we did was we created a no touch button where when you went to hover over the photoresistor, it simulated a button that you didn't want someone to touch, and it would play a tone as well as light up a pattern. And I believe I used the Mario theme in my video to show you guys. There was also a second coding challenge I didn't end up completing here, which basically just says, as you can see here, replace the 10 kilo ohm resistor with an LED. So alter the circuit by replacing the 10 kilo ohm resistor with an LED. The negative leg should connect to ground, and then see what happens when you place your finger over the photoresistor. It says this is a great way to see Ohm's law in action. So we didn't actually do that in the last video, and before we get to circuit 1D, we'll just do that quickly. Okay, so this is the previous circuit. So right now in the previous circuit we had it hooked up just as a night light. When the light level got darker, the LED turned on. That was circuit 1A, or sorry, 1C. And now the light level is so bright I can't even turn on the circuit that way. And so right now we're reading a light level of 922 because this overhead light is fairly bright, and even when I cover all the way, I only get down to 600, which doesn't quite meet my threshold, which is why this is not turning on. Because when I did it before, I had this sort of light condition where I started off at 600, and then when I covered it, I met my threshold. But that's just a matter of adjusting the threshold, and it depends on the light that you have in the room. And now that I got this overhead light, my light levels have changed significantly. But let's unplug the circuit for a minute and do that second coding challenge. We're going to take out this photoresistor here, this resistor here that's in conjunction with the photoresistor in this voltage divider circuit. So we'll take that out. That's a 10 kilo ohm resistor. We'll just set that off to the side. And we'll replace it with an LED. So make sure that you take the negative lead of the LED, which is the shorter leg, and connect it into ground, and the positive lead attach back into the center. The positive lead attach back into the center with your photoresistor as part of the voltage divider circuit. Now you notice the negative lead I didn't actually connect into this rail here, which connects to ground, because I am going to attach a 300 ohm resistor with that LED, and that's just because as we learned already, you should always place a current limiting resistor in with your LED. Otherwise too much current can flow through it, and you will have a very bright LED for a very little bit of time, and then it'll burn out. So we're just going to put that current limiting resistor in that, and I'll explain that why in a second. But in the meantime, let's plug that in and see what happens. Okay, so I'll try to move this. I'm not sure if you can see there, but the the LED is lit up. We see we have a reading of about 560, around there, of light level. So again, we're still reading the light level from this voltage divider through this yellow wire, which is going into our analog A1 pin, I believe, or A0. It's one of the analog pins. And so there's still the voltage divider circuit here, but the only difference is here is we have this LED lit up. So what's exactly happening? Well, what is happening is we replaced the 10 kilo ohm resistor in the original circuit, which was, the 10 kilo ohm resistor and the photoresistor were forming a voltage divider, and now we've replaced it with an LED. But an LED has a couple characteristics associated with it. The main one that's of importance for us is that it has a voltage drop. So LEDs have a voltage drop of anywhere from 1.8 to 2.2 volts, or in or around there, depending on the color of the LED. I'm not exactly sure the voltage drop on a blue LED. I know red LEDs are typically around 2 volts. I think blue LED might be a little higher. But what that means is it's kind of like a threshold, meaning no current will flow through the LED until there's at least the 2 volts of going through the LED, and at that point the LED will light up. So you need that minimum amount in order to light up the LED. So that's one important characteristic here. So obviously there's at least the 2 volts going through the LED, otherwise it wouldn't be lit. Another thing that's apparent is in highlight conditions, let's just turn this on, the LED is fairly bright. I mean, it's fairly bright here in this light level because there's a fair bit of light in this room. And that reason being is because in highlight conditions we know that the photoresistor has very low resistance. So therefore there's a lot of current that's able to flow through the LED, therefore lighting it up, even with our current limiting resistor that we put in place. Whereas if you get lower light conditions, you can see that the blue LED dims there. Hopefully I'll try to make it in a way that you guys can still see it. I'll lift this up a little bit, and I'm unplugging everything. Okay, so as I make the room darker by covering this thing, you'll see that the LED gets dimmer. It's really hard to show in the video here, I think. But again, highlight conditions, bright LED. As I cover the photoresistor and gets darker, the LED dims. Hopefully you're able to see that. Basically what's happening is I cover the photoresistor. We know in dark conditions the photoresistor's resistance shoots up. So therefore if the resistance shoots up, there's less current going through the LED. And this dates back to Ohm's law, which we talked about earlier, where voltage equals current times resistance. But we could have rearranged that formula to realize that current equals voltage divided by resistance, or conversely, resistance equals voltage divided by current, which says that current and resistance are inversely proportional. If you increase one, you decrease the other. So if I increase the resistance by making it darker in the room, i.e. covering the photoresistor, the current lessens and the LED doesn't become as bright because there's less current going through it. So again, increasing the resistance of the photoresistor decreases the current going through the LED. And if I took out this current limiting resistor, it would no longer be connected to ground, but if I had it directly connected in to ground here, it would probably be a little brighter. So right now it's not hooked up to ground. You're not really supposed to fiddle with things in live wires, but I understand that there's no safety issue with that, so I just did that. You might have been able to tell that it got a little brighter without the current limiting resistor. Not much, but a little bit. But we'll still have the same effect where, again, if I cover the photoresistor, the LED is going to get a lot less. So this just basically gives you a visual cue of how the voltage divider is working and the relationship of Ohm's law. In bright light, the photoresistor has very low resistance, therefore allowing a lot of current to flow through the LED, which is why it's so bright. And in dim light or darkness, there's high resistance on the photoresistor, therefore dimming the LED because less current is able to flow through it. And again, you can see that there's less output at the voltage divider over here in serial monitor when I cover things up. Anyway, but we'll get on to circuit 1D because that's what we're actually here for. So let me just get rid of this. And so we'll quickly get back to the. So we did the coding challenge. Now we're going to go to circuit 1D. A couple troubleshooting issues. If you weren't seeing anything on the serial monitor, again, as usual, make sure you're on the right port. If the light never turns on or is always on, adjust your thresholds. We've seen that in the code. If depending on the light level in your room, the threshold is different. So basically, when you're just in the room, when the light's on and you're not anywhere near covering the photoresistor, see what the light level is then that you're reading, and then fully cover the photoresistor and see what the light level is then, and make your threshold somewhere in the middle there. So that's just something you're going to have to play with on your own. And so now we've completed circuit 1C, and we'll move on to circuit D, which is making this RGB nightlight. So the RGB nightlight, again, RGB is a special LED, just stands for red, green, blue LED. And it's really just, it's a single LED, but it's just 3 differently colored light emitting diodes, LEDs, built into one component. So these 3 colors can be combined to create any color of the rainbow. So we're going to need this RGB LED, we're going to need a photoresistor, which we already have. We're going to need 3 30 ohm resistors, and that's because there are 3 separate LEDs in this one LED, hence why this LED has 4 legs. There's one common ground, and then the positive leg for the red, green, and blue LED. So we need 3 separate current limiting resistors for our LEDs, and we need a 10 kilo ohm resistor, again that is still with the photoresistor. As well as we're going to need a potentiometer, bring that back, which we used. So the RGB LED, it's actually 3 small LEDs, 1 red, 1 green, and 1 blue, inside of a normal LED housing. And there's the same ground wire for all 4 LEDs. And so it's this long lead is the common ground, which is kind of ironic because in all other LEDs, it's the short leg that's the ground, but in this RGB LED, it's the long leg that is the ground. Don't forget the current limiting resistors. As we said, you always want to have a current limiting resistor with your LEDs. So don't forget that. And you're going to turn on more than one color at a time. That's what the RGB allows you to do. Blend colors together to create a new color. So we are going to be using PWM pins this time. I mentioned PWM pins before. They're the pins 3, 5, 6, 9, 10, and 11 on your Arduino compatible boards, which includes the red board here. And with PWM pins, you can use analog write. So whereas all the pins, all the digital pins, you can use digital write and write either high or low to your pin, turning on or off something, basically sending either 5 volts at high or 0 volts at low. But with analog write, you can send any value between 0 and 5 volts because you can send an integer from 0 to 255 in the analog write function. And so basically that allows you to do analog output instead of just digital output, and it's accomplished through what's called pulse width modulation. So whereas digital write, you can only write commands high and low, basically turning the pins on 5 volts or off with 0 volts, turning an LED on or off, let's say. With the analog write command, you can output 2.5 volts by quickly switching on and off the power, sending that to the pin so that it's only on 50% of the time and off the other 50% of the time, effectively giving you 2.5 volts. And by doing this, you can really have any voltage between 0 and 5 volts can be produced using this pulse width modulation. So you can create many different colors on the RGB LED light, and it's a kind of a cool project. So what we're doing here is you're going to hook up your RGB LED into your circuit as you would kind of any other LED. You have the common ground pin here connected to our negative bar of our breadboard, which is then ultimately connected to ground of the microcontroller. And then you have each of the other individual LEDs housed in this RGB LED connected to pins 9, 10, and 11. So again, The flat edge indicates where the red LED is. So look on your LED and see the flat edge. That'll be the red LED, and then there's the common ground, and then you have your green and your blue LED. So indicated by the red, green, and blue wires that are hooked up over here on pins 9, 10, 11. And you'll notice that all these pins are pulse width modulation pins because they all have this little tilde symbol next to the pin number. So that's only on pins 3, 5, 6, 9, 10, 11. So we also hook up a potentiometer. Again, one end of the potentiometer, one of the terminal pins, is connected to ground. The other is connected to 5 volts because the 5 volts from the Arduino is connected to this power rail. And then the middle pin, or the wiper, is connected to one of our analog reads, in this case analog A1. And then we still have our voltage divider circuit with our 10 kilo ohm resistor and photoresistor in this configuration here, creating a voltage divider where one end of the voltage divider is connected to 5 volts, the other end is connected to ground, and then the middle connection, the common connection between the resistor and the photoresistor, is connected to one of our analog inputs, in this case A0. So basically we're using the potentiometer as a variable voltage, a variable resistor that we control via the knob, and then this voltage divider kind of creates a variable resistor, but that's controlled by light levels. And we're just going to go find the code and upload it. Again, the code is available on the SparkFun Inventors Kit website. And this is kind of the general overview of the program. We're going to store the light level from pin A0 into a variable photoresistor, which is what we've done before. I've called it photoresistor, I've called it light level, but we're going to store whatever the light level is in some variable. We're also going to store the reading from the potentiometer on one of the analog pins, which we've done before. And then if the light level variable is above the threshold, we're going to call a function that turns the RGB LED off. That's what we did before. If our light level was above a threshold, meaning it's bright, we didn't have a light on. And if it's below a threshold, we're going to turn the LED on. In this case, we're going to turn the RGB LED on. And then the potentiometer is used in the circuit because it's going to control what colors we turn things on. If the potentiometer is between 0 and 150, we're going to have the RGB LED be red. If it's between 150 and 300, orange. Between 300 and 450, yellow, and so forth. Green, cyan, blue, magenta, depending on the value of our potentiometer. So basically, as we turn the knob on our potentiometer, we're controlling what color the LED lights up when it's dark in the environment. So this is the code that we're going to note. But first, before we do this, as always, let's go and just look at the code. So again, I downloaded this directly from the SparkFun Inventors Kit webpage. And yeah, so let's just go through it quickly. As usual, they have comments here that let's just make this big and read through this. So as usual, they have comments just explaining what the program does. In this case, this turns an RGB LED on or off based on the light level read by a photoresistor, and we can change the colors by turning the potentiometer. So again, the RGB LED is going to turn on in dark conditions, and it's not going to be on in light conditions, but what color it turns on in those dark conditions will be based on how we adjust the potentiometer. As usual, we have all of our variables that we require. In this case, we have a variable for photoresistor, which is the variable for storing the photoresistor value or the light level. We have a variable for the potentiometer, again storing the value that we're going to read in from the potentiometer, which is going to be anywhere from 0 to 1023, depending on where we adjust the knob. And our threshold, which is if the light level goes below this threshold, below 700, we're going to turn the LED on, the RGB LED on, and if it's above, we're going to turn it off. As you can see right now, based on the previous code that I had loaded up here, which is not related to this program, it's related to the circuit 1C, but the serial monitor is just reading what the current program was showing. The light level is only 500 and some right now. Now if I turn this light on, I still only go up to 560. So this threshold is obviously not going to work because this is going to have the RGB light turn on no matter what. So we might want to adjust that right now. One of the reasons actually that might be, I'm just looking, this is an error. I've still got the LED hooked up in this voltage divider circuit, which we used as one of the coding challenges. So I'm just going to take that out and replace it with the 10 kilo ohm resistor originally in there, which will change our light level that we're reading. And that might make it a little more normal. So now the light level is almost 1,000. So the threshold of 700 probably will work. Let me cover it up. Yeah, so when I fully cover the photoresistor, the light level does go below 700. Just barely, but it does go below. If I turn off this light, I'm almost at 700 right there. And then when I cover it, I go a lot lower. And I obviously meet the threshold that was in the previous circuit, I guess, which is why that light turns on. So that should work now. So we'll go back to the code. It's just some things we made changes and forgot to change it back. So going forward with that, I'll just get rid of this for now. We have our threshold, and then we have we've created some variables for our LED pins to connect to. So red pin, green pin, and blue pin will be on pins 9, 10, 11, respectively. These are all pulse width modulation pins. And again, in this code from SparkFun website, they're just using regular variables as our pins, which is good because that way in pin mode here, and whenever we want to use these pins, we don't have to refer to just the magic numbers 9, 10, and 11. We can refer to red pin, green pin, and blue pin, which is more exclusive. However, I don't like that they just use variables here. I think they should have at least made them constants by putting the keyword const in front of each of them, just indicating that no one can change these down the road. I can't, in the code, change red pin to be 7, which wouldn't work because we know it's on pin 9. So using constants is probably the better route, but they didn't do that. Also, we could have just used hashtag defines. That's kind of a little older version, but hashtag define red pin and make it 9. Either of these options would have worked, but I'm just going to stick with the code that you guys will download from the website. So it just uses these variables, which are used down in setup to set up our pin modes. We set up all 3 pins as outputs because they have LEDs on them. And we also set up our serial communication as normal. In the loop, I have, I guess I've commented these out. I had these analogs switched at one point, so I don't really need this commented code out in here. I think actually, now that I think about it, the reason I have that commented out is when you download the code, I believe they have the photoresistor on A0 and the potentiometer hooked up to analog pin A1, which is likely what you'll do if you just hook up the circuit directly. Because I was doing other things with it, I end up just having my photoresistor on A1 and my potentiometer on A0, so I just commented that out. Just, doesn't really matter which analog pin your photoresistor is on versus your potentiometer, just make sure that they're on the right one. So again, we're just going to read in our light level values on our photoresistor variable and our potentiometer value in the potentiometer variable. And then we're going to print everything out to the serial monitor. So we're going to print out the photoresistor value, which is our light level, and our potentiometer value. And then here's where the actual logic of the code comes in. If our photoresistor is below a threshold, i.e. if the light level is below the threshold, 700 in this case, if it's dark, the photoresistor value is going to be below that threshold, and we're going to turn on the LED. And then we're going to use nested if statements to check for a variety of ranges and call different functions based on the current potentiometer value. Those functions are found at the bottom of the sketch. So basically, we're only going to come into this if statement in general if the light level that we're reading in on the photoresistor variable is below the threshold, 700 that we've created. And then once we come into this code, then we're also going to have other if statements that decide what we actually do. If the potentiometer value is greater than 0 and the potentiometer value is less than 150, so this is a logical Boolean AND, if both these conditions are true, the potentiometer is greater than 0 and less than or equal to 150, I'm going to call a function called red, which presumably is going to turn on, make the LED be red. If I'm greater than 150, if my potentiometer value is greater than 150 and less than or equal to 300, I'm going to call a function called orange, presumably making the LED orange, and so forth. I have got different ranges. If I'm 300 to 450, I'm going to make it yellow. 450 to 600, I'm going to call green. 600 to 750, call cyan. Greater than 750 and less than or equal to 900, blue. And finally, if the potentiometer value is greater than 900, I'm going to call magenta. Or for everyone with 16-bit color like myself, purple. So these functions are all functions that we user-defined functions that are created below, but they're essentially just going to turn the RGB LED to that color based on the range that, depending on where you have the potentiometer. And if the photoresistor value is never less than threshold, meaning it's bright in the room, then we're going to turn everything off. So we're going to call the turn off function, which is going to turn off the RGB LED. And then, as usual, we're going to have a delay in here of 100 milliseconds, so 1/10 of a second, just so that we can see the printout good on the serial monitor without just going too quick. And then these are all the functions. They're all about the same. For example, they're all void functions, so they don't return any values and they don't take any parameters. Red simply calls the analog write function 3 times, once on each of the 3 pins, on the red pin, the green pin, and the blue pin, and it passes in as its second argument, a value representing how much voltage to send to that particular pin. So if we want, for the red function, where we want full red color, we pass in 100 as our second parameter to the red pin, and we don't pass anything on the green and blue pin. So we don't want any green and blue color, we just want full red. And we've passed in 100. Now, passing in 100 is just going to make the LED not as bright as it could be, because again, that's less than half the voltage. It's about 2 and maybe 2.5 volts. If we passed in 0, like these colors, we're having no color, 0 voltage going to those LEDs. If we passed in 255, we'd have really, really bright red, but 100 is kind of just less than halfway. But either way, the color will only be red. It just won't be as bright red as it could have been. For orange, we need a mixture of green and red, so we're passing in more red because we're passing in 100 out of the 0 to 255 range to red, and only 50 to green. But again, mixing that little bit of green with red will apparently make orange. And then if we have equal amounts of green and red, then we have yellow. This is taking us back to our kindergarten days of mixing colors. If we just write to the, if we do an analog write to the green pin, 100, we're just passing in, and we leave the red pin and the blue pin both at 0. Again, we're having full green color. Cyan is equal mixtures of green and blue. Blue is just blue, with both other LEDs having 0 volts sent to them. And purple is equal amounts of red and blue. And turn off is just turning them all 0. So we're doing an analog write of to all 3 LED pins with passing 0. We could have ultimately just wrote these as digital writes as well, passing low or 0 to them. So we could have just done digital write of red pin low, and done that for all 3 LED pins as well, because whenever we're doing something 0 or 255, like full or 0 volts or 5 volts, we could just use digital write as well. But makes sense just to stick with analog write, because that's what we've been doing. So that's that code there. Let's just quickly upload it and see if it works. So again, this is the code that you download directly off of the SparkFun Inventors Kit website. Uploading the code. And as you can see here, the photoresistor value is almost 1,963, and our potentiometer value is at 255. So let's just go look at the range quickly. So at 255, we'd be in this range here. Our potentiometer value is between 150 and 300. So if we cover up that photoresistor and make it dark, thereby going below the threshold of 700, the RGB LED will turn on, and it should, according to the range here of where we have the potentiometer, it should turn orange. It should call the orange function. So let's see if that works. Let's shut off this LED, and now our photoresistor value's just above 700 now, so it's not going to take much to turn it on. Oh, you know what I just realized? You'll notice I don't have an RGB LED hooked up. I forgot to hook it up. So I got this RGB LED in that 37-in-1 kit that I bought, which it's the exact same as just a single RGB LED. It's just that it has all the pins in this little module. So it's got a common ground pin is actually off to the side here. This is the common ground, denoted by, there's a, I'm not sure if you can see it there. Let me just turn this light on. There's a negative sign right here for the ground, and then there's RGB on these pins, red, green, blue on these pins, which I've hooked up to these wires, and I'll hook that up into the circuit. So I should probably look. So I've got the red pin should be on pin 9, the green on pin 10, and the blue pin on pin 11. So I'll just hook this up into the circuit here. I'm just going to have to unhook this. So I'm going to shut everything off, and I'm going to take these pins out along with these pins. So this is all associated with the LCD, so I'm unhooking that, and instead I'm going to hook up the RGB up into 9, 10, 11, and the ground pin into ground. So this is going to be the RGB pin. So it's going to work the exact same as if you had the individual RGB LED, which I have here. So I originally had it hooked up here. Again, you can see the 4 individual leads. So the second lead is common ground, which I've hooked up to here, the black wire, and then RGB. I could hook this one up as well, but this little module is nice and just convenient. So I don't know if you can tell, that's kind of like an orange color. So depending on the way it hits the camera light, it looks orange, but you can kind of see right there that's an orange color. If we change the potentiometer value, which I'm going to do right now, we should see a change based on the ranges. So keep in mind that those ranges, and as I change the so I'm turning the potentiometer value all the way to 0, so that RGB LED got turned red again. It might be hard to see in the video. And as I increase the potentiometer value, and again you can look in the serial monitor over on the screen there. I'll make this a little bigger. It's going really quick, but you can see the potentiometer value is around 70 right now, so we're still in that original range where the RGB is going to be red, and I'm still below it, and then I just flicked above 150. So when I flick above 150, I kind of turn into that orangey color. As I get above 300, I should go yellow, so now I'm above 300, and then I turn green when I'm above 450, so I'm now green. When I go above 600, I turn into cyan, which is kind of this bluish green. Nice color there. When I get above 750, I turn just blue right there. And then when I get above 900, I turn into this purple magenta color. And again, it looks good from where I am purple, but in the video it doesn't seem to be showing very well, so I'm not really sure what's going on there. But that's from my vantage point, that's nice and purple. And so yeah, it seems to work. But again, it does need to be dark. So again, if it's light in the room, if I'm above the 700 threshold, which you can see over here, then it won't light up, and it's only going to light up if it gets dark. And what color it turns is going to be based on that potentiometer. So that's the regular project. But as usual, we're going to do the coding challenge. So we're just going to stop this for a minute. And I've got the coding challenge already up here. But before we get right to the coding challenge, let's see what the coding challenge is. Well, first of all, what do we do in that last code for circuit 1D? Again, we dealt with analog output, and we used pulse width modulation to send anything from 0 to 5 volts to those pins. Thereby, instead of just using digital write, we're able to have a multitude of colors using that RGB LED. We use nested if statements, which are just if statements within if statements. That's why we were able to have the if statement that said if our photoresistor value is below the threshold, meaning if it's dark, then we're going to turn on the RGB LED. But then we had several if statements to say what color the RGB LED was going to get turned on based on the potentiometer value. So that's nested if statements. And we use some more logical operators, like we use Boolean AND to determine the ranges. This wasn't absolutely necessary, because we could have just done if the value is less than or equal to 1. Oh, actually, it probably was necessary. Scratch that. We declared some functions, user-defined functions, by defining our own functions using this syntax, and then we called those functions as well. So the coding challenge is we just want to add more colors to the RGB. We want to use the analog write function to blend different values of red, green, and blue together in even more colors. And we want to divide the potentiometer value and make more nested if statements. So basically just increase the range. I'm not sure how much fun that is, especially considering my camera doesn't really show the full spectrum of color that I'm seeing here with the RGB. So, but there is this I wanted to do. Multicolor blink. Try using delays and multiple color functions to have your RGB change between multiple colors when it's dark. So basically, instead of just having a color set by the potentiometer, when it goes dark, I want to be able to flash the LED like red, blue, green, yellow, and kind of repeat that pattern. I want to be able to change the threshold. So I want to try setting your threshold variable by reading the value of the potentiometer, and then by turning the potentiometer, you can then change the threshold value and adjust your night light for different rooms. As opposed to where I actually had to change the threshold in code, we want to be able to change it via potentiometer. And then I want to have a fading. I want to cause the LED to fade, have this fading effect, where I use analog write to get your LED to pulse gently or smoothly transition between the colors. Whereas before, there's no smooth transition. It went from red to orange to yellow to green, cyan, blue, and magenta as soon as we got into that range. So there was like only 6 or 7, correction, there was only 7 ranges, so there was no smooth transition. We just went from red to orange. There's no blending. So let's see if we can do that. So this is my code challenge code. So again, as usual, I've got some comments here, and the double asterisk indicates this is a Doxygen style comment, and I've got these little tags, @file, @brief, all that stuff. We've kind of explained that before. These are all, a lot of the stuff is the same as the other code, so these are all my constants. I've made them constants as opposed to ints. My constants for my photoresistor pin, my potentiometer pin, those are both on your analog A0 and A1, and my pins for the RGB LED, which are going to be on the pulse width modulation pins 9, 10, 11. Again, this is just, let me put that back actually. The syntax is just required for that generating HTML documentation, so disregard that. I've got the threshold still set at 700. If I need to adjust that, I can now, but it'll be via the potentiometer. In setup, I've got I call pin mode function, basically set up my RGB LED pins as outputs, and then in the loop I do analog reads to get my light level value from my photoresistor pin and my potentiometer value from the potentiometer pin. And then here's where I'm going to dynamically adjust the threshold based on the potentiometer. I'm going to call the map function. What the map function does is it takes in some value, in this case whatever value I read on the potentiometer, and then it takes in the next two parameters are the range that that value should be through in. And we know the potentiometer value will have a range of 0 to 1023 because the analog pins, that's what they read. They have 10-bit resolution, and they can read in values from 0 to 1023. So I put in the value in the map function, and then I put in the two values, the minimum maximum values associated with the range of that value, and then I put in two values that I decide that I want to now be the minimum and maximum. So basically you're mapping a potentiometer value from 0 to 1023 to a value now of 200, 800. That directly corresponds with the 0 to 1023. For more information on the map function, just Google Arduino map function, and it'll explain it in a lot better detail than I just did. But essentially I'm now I'm using my potentiometer value to map the threshold, so that can be anywhere between 200 and 800. Then I'm, as usual, going to print off all my values to the serial monitor, both the light level value, the potentiometer value, and the threshold. And then if the light level is below the threshold, again, light level I'm using, whenever I make the code, I use light level. They use photoresistor, same thing. But if the light level is below some threshold, the LED behaviors in low light. So what do I want to happen in low light or in darkness? Well, I want, if the potentiometer value is less than 512, so if the potentiometer value is less than halfway, I want to call the fade colors function, which is just the smooth color transition function I created. Else, I want to call the multicolored blink function, which just blinks, has a multicolored blinking effect. So again, both of these are nested, both of these if statements are nested within the main if statement here. So both of these possibilities only happen if the light level is below the threshold, meaning if it's dim light or dark in the room. And then I decide on whether I call the fade colors function or the blink LED function based on the potentiometer value. If it's less than halfway, I'm going to do fade colors. Greater than halfway, I'm going to do the multicolor blink. And if it's not dark at all, I'm going to turn everything off. So turn off the LED in bright light conditions. As usual, I'm going to delay 100 milliseconds so that it allows for readability in the serial monitor. And here's the two user-defined functions I created. So fade colors just smoothly transitions between colors on the RGB. So I use a for loop to go from 0 to 255, and I just change, I call analog right, and I'm using the index of the for loop, so the I, to affect the colors. So the red LED just gets passed in I, so that is literally going to just go from 0 to 255. So I'm going to go from the red LED being off to being fully on, and then the green LED is doing the exact opposite. It's 255 minus I, so the first time it's going to be minus 0, which is just 255, and at the end it's going to be 255 minus 255 at the end of the for loop, which is going to be 0. So it's doing the exact opposite. It's going to start off at full brightness and decrease to off. So the red LED is starting off, going to full brightness. The green LED is full brightness and going off. And the blue LED is increasing, but gradually, because I'm constantly going to be dividing I, the index, by 2. So it's going to gradually increase brightness, but it's only ever going to be able to get half brightness. Because when I is 255, well, 255 divided by 2 is like 127, so I'm only going to be at half brightness. And again, I just have a delay of 10 milliseconds so I can adjust the speed of the fading here, this delay. This is just to make it look good. I can increase or decrease that. It's up to me, or you as the programmer. This multicolored blink function, simply I use the set color functions we created before, and you can find that's typically a user-defined function people create when they're using these RGB LEDs. You can find lots of tutorials online for that. But I'm basically just blinking between having a red color on for half a second, a green color for half a second, a blue color for half a second, and a yellow color for half a second. And again, red is, again, these three arguments represent red intensity, green intensity, blue intensity. So when I've got full red intensity and nothing for the other two colors, I'm red. Full green intensity, nothing for the other two colors, I'm green. And full blue intensity, nothing for the R and G values, I'm blue. And then when I have, full intensity for red and green and 0 for blue, it's yellow. But again, that's just, you can Google that. And this is the set color function. We've seen this before. Again, it's what's actually causing the color. And then turn off, it just turns everything off. I actually just called the set color function this time, passing in 0 for everything. Last time I used analog write, and I just called analog write 3 times, setting all these values to 0. I also could have used digital write and set them all to low, but this just makes it a little nicer now, because if I already have this set color function, why not just use turn off to call this function? Anyway, let's upload this code. As usual, this video is way longer than I thought. So, as you can see, the light level right now is 861, which is well above the threshold of 700. So I'm not going to turn on the light until I go below that 700. The potentiometer value is almost fully turned all the way up at 1000 and roughly 1000, which means even when the light level goes below, at this point I would do the multicolor blink, because remember, the fade colors function only happens if I'm below 512. And then the threshold, that's just a call, just 1 second. And then the threshold is 791. So that threshold is what I've changed. So the threshold is not 700 like it shows up in the code. It's actually at 791 because it's being mapped based on the potentiometer value. So if I adjust the threshold by adjusting the potentiometer value, I adjust the threshold to just about 800, 790 some. The light level is still 800. If I shut the light off, now it got dark, so now the threshold is still around 800, but the light level is like 600. What I have happening now is I'm blinking the LED, because I'm now below, my light level is below the threshold based on my potentiometer, but because my potentiometer value is above 512, according to my code right here, I'm only going to call the fade colors if I'm below 512. Right now I'm calling the blink color, so I'm going to go from red to green to blue to yellow. And that's what's happening. I'm not sure how well those colors again are showing up on the screen, but they're working here. Now if I bring the potentiometer down below 512, keep an eye on the potentiometer value. I'm bringing it down to now below 512. I've affected both the threshold and the potentiometer value, so the threshold is now a lot lower too. But now, if I do get it dark enough by getting below the threshold, because I'm below 512, I have this fading effect now. You can see that the colors are fading just between different colors. Again, it's probably really hard to see there. I realize how crappy this camera is. But there's more of a fading effect. It's not just blinking red, green, blue, yellow. It's doing this kind of fade in and fade out. And I like this actually a lot better. But anyway, that's the code. Again, sorry for the long video, but that's the last circuit. Obviously, if you ran into any troubleshooting in circuit 1D, again, if the LED never turns on or off, make sure that the photoresistor values are the photoresistor is returning values between 0 and 1023, and change the threshold. So again, adjust the threshold so that when it's dark, you actually go below that threshold. If your LED doesn't show the colors that you expect, make sure that all 3 pins are driving your RGB LED are set to output using the pin mode command. So if you forget a pin and it's not output, well, it's not going to be involved in your color scheme. And if nothing is printing the serial monitor, try unplugging your USB cable and plugging it back in. The standard thing, hey, it's not working. Did you try turning it on and off again? Do that. Anyway, thanks for watching.